In this video, we are going to discuss about the tree data structure. The prerequisite to understand this video is the knowledge of array, and the knowledge of linked list. Having knowledge about these two topics will make understanding easier about the tree data structure. Tree is a non-linear data structure available in any programming language in order to solve problems. Generally, if the data possess certain relation among themselves, then we go for a tree data structure. For example, let us consider the designations in an university. The university system, there is a vice chancellor, then we have deans, then head of departments, then professors. And in general, all deans, they report to VC. Say dean engineering, dean management. And all deans, they have HODs of various departments, and these HODs normally report to the dean. Similarly, HODs for the management departments. And all department HODs, they have a set of professors. Professor 1, Professor 2. If we want to implement this hierarchy in a program, then the tree data structure would be the best choice for implementing this problem. Because normally the tree will have a node which will point to the elements in the next hierarchy, and this element also points to the elements of its next lower level, and these are called the hierarchy of nodes. So here, if I write down VC here, then the deans will be coming here in this hierarchy, and HODs will come here, HODs will come here, HODs will come here, HOD, and then professors will be in this level. So if you consider if we consider this one as a tree, then this one is called the node in the top level, and these are the nodes in the next lower level. Then this one is the node in the next level, so on so forth. We need a data structure in order to represent this existing hierarchy of designations. If we observe this data structure carefully, then we can see that a VC is a node which is in the top level, and VC is connected to two deans, dean engineering and dean management. Dean engineering is connected to three HODs. These are three different, represented by three different nodes. HOD CSE is also connected to three professors. Again, they are represented with the help of different nodes. So if we see the hierarchy, this one is in the top level hierarchy. This is the top level hierarchy. This is the next level. Then it goes down till the last one. And professor, they do not have any other connecting nodes. And this is the last level of hierarchy in the tree architecture. So if we want to represent this hierarchy in the form of a tree, then what we need to do? Let us consider a single node here. This node, we can see that it has some data or information, That information is the designation, and it has two pointers that points to the two deans. This is pointer 1, this is pointer 2. Similarly, dean engineering is the designation of the post, and then it has three links, 1, 2 and 3. Both three links are pointing to three different HODs. And then the HOD CSE, it has three links. The data here is HOD CSE, the designation, and the links are, it links to Professor 1, Professor 2 and Professor 3. If we want to represent these nodes in a program, then what we need to do, we need to write a structure. Let me say structure and say node, let me tell node org, that is node that represents one organization. This is a random name I have given. So it has three components. The first component is say character array, and the name of that field, let us say this is designation. Say we will take 20 characters here. We have one pointer. That pointer is point to the first dean engineering. Then one more pointer, let me say the pointer 1. Let me say pointer 1. If I see here, this pointer is pointing to another node, and that node has the same structure or same attribute as the previous one. That means the structure in the tree, structure of each node is identical. That's why it should point to another element or another node of the type struct node org. Similarly, we have another pointer 2, then that pointer is also point to another element node org. And if I can see, we have maximum of 3 pointers in the tree. First one is the Professor 1, second one is Professor 2, third one is Professor 3. In Dean also we have 3 pointers. Since all the nodes need to be identical, that is why for each of the node we must have to have 3 pointers struct node org ptr3. Each of the node should have 3 pointers, 1, 2, 3, and one information or data field. That the information field will keep the name of the designation, and rest of the 3 fields or 3 members will keep the address of the elements in the down level hierarchy of that particular node. If I redraw these 3 in the form of nodes that can be represented with the help of a program, the first one will be VC. Say we have VC here, then we have one pointer, the second pointer, and third pointer, 3 pointers. This field is called designation field. The first one, designation field. Second field is the PTR1, then PTR2, PTR3. Then similarly, Dean Engineering and Dean Management, say we'll have to create another 2 nodes. This node represents the Dean Engineering. This node represents the Dean Management. And the information here will be, say, Dean Engineering. Let me write down in short. And it will have 3 fields again, 1, 2, and 3 pointers. Similarly, the Dean Management, say DM, Dean Management, short representation of Dean Management, then 1, 2, and 3. In the first node, the VC, where we have 3 pointers, one pointer will point to this one, second pointer will point to Dean Management, and third pointer, since we do not have any third dean, that's why it will be null. And if we consider the address from programming point of view, suppose that address of this node is say 100, address of this node is 200, address of this node is 300. In that case, 200 will be stored here, 300 will be stored here, and this field is null. Similarly, HOD CSE and HOD EC, HOD EE, these are three nodes under the node of DIN engineering. So we'll create another three nodes here. The same structure will be followed in this level also. It will have three different pointers and one designation field, say HOD CSE. Then second one will be HOD ECE, HOD ECE, and then three pointers again. And third one will be the HOD EE, and there are three pointers again. So here, if it is say 400, this address is 400, this address is 500, this address is 600, then this will point to the first element, this one will point to the second one, and this one will point to the third one. And this field will carry 400, this field will carry 500, and this field will store 600. Since DIN management have no department, that is why all these fields will be, pointers will be null. Then this process continues and we will draw the professors here, the next level nodes in this level here, and all the pointers from the upper layer will be connected to these nodes. And these are professors. Similarly, there is no elements here, no next level elements, so pointers will be null, and the information field will have the professor P1, P2, P3 in that way. P2 and these 3 pointers are null, P3, these pointers are null pointers. Then this is the tree which is being created, or which could be used to represent the hierarchy of the designations that we have in our problem. So this is the programming level implementation of the data that need to be stored in the in order to solve the problem. So the benefit of this tree, how many DINs are there under the supervision of the VC? Then what we can do, we will go to the node representation of the VC, then we will follow the first link. If I go follow the first link, we'll go to location 200, which is given by this address. Then we'll see that DIN engineering is one of the nodes. So VC is connected to DIN engineering. Then we will follow the second link. Then we'll see that the DIN management is also one of the DIN under the VC. And if we go to the third one, we can see that this is null. That means there is no more DINs available under the VC. So there are two DINs under VC, and if I follow any link, say suppose I want to see how many HODs are there under DIN of engineering, and we can follow this node and we will go to the first link. We can see the head computer engineering is under DIN engineering. Then we'll follow the second link, HOD electronics ECE is one more head, and then the third one is HOD electrical engineering. So there are three HODs under DIN of engineering, and if I go to the DIN of management, then we can see all pointers are null. That's why there is no HODs under the DIN of management. So that way we can represent the data structure, or we can represent the data, which is the organizational designation hierarchy, and with the help of a data structure. And the data structure, the best data structure that we can use for this problem is the tree data structure. Now let me take another example for using the tree data structure. Suppose that we have few numbers to be processed, and we want to store the elements, store these numbers in the memory in such a way that we can search any item or any digit or any number in a fastest possible way. So suppose the elements given here are 7, 10, 16, 9, 11, and 5. Suppose that these are the elements. Different choices we have to store these data. One simplest example is to store these elements in an array. However, if I say I wanted to search the element 9 in the array. So what we need to do, we need to read, or we need to scan each and every element of the array and to compare is it equals to 9 or not. So if we do that, time taken to search the element a bit high. The same thing can be represented with the help of linked list. First element is 7, the next element will be 10, third element will be 16, then 16 will point to its next element 9, then 9 will point to next element 11, then 11 will point to next element 5, and 5 will point to null. So here also, if I want to search element, I need to read the element, read all the elements sequentially like as it is in the array. If we opt to store these elements in a tree with a condition that we will create a tree, but however every element in the tree will have some relation. The relation is any element which is to the left of the node will be smaller than this node, and to the right of that node will be greater than this element. So if we follow that relation, if we follow that norms, and if we create the tree, then it will look like first 7 will be the first node, say, then 10 is greater than 7, so 10 will go to the right side of 7, and 16 is greater than 10, so it will go to the right side again. Then 9 will be go to the left of 10, 11 will go to the left of 16, 11 will go to the left of 16, 5 will go to the left of 7. Now this is the tree. So suppose I wanted to retrieve 9, we wanted to locate, or we wanted to find 9. This is called searching of 9. So if it is 9, then this is 7, so 9 is greater than 7, so 7 it will go to the, it will follow the right link, it will come here, and 9 is smaller than 10, then it will go to the left side, and this is 9. So here, compared to earlier array or linked list, the searching of 9 or any element will take less time when we store it in the form of a tree. This is another example of using another application where we mostly prefer tree. And in order to implement this tree, again what we will do, we will declare one structure, struct, say, elements. Then in this structure we will define one member, integer data, and we can see here we have two links in every node. So we'll declare one pointer, struct element star, let me say this time it is left, and next one will be struct element right. So these are two pointers in the structure. So if I draw this 7 here, if I draw 7 in the form of a tree or in the form of a node ELE, then it will look like the first element will be, it will have two pointers, and 7 will be here, and it will point, left will point this side, right will point this side, and again they will point to another similar nodes. And second element 5 will be here, this pointer, there is no element in this side, that's why this pointer is null, and there is no element in this side, there it is null. On the other hand, 10 here, 10 will come here, and it will again have two pointers and one information. So 10 will be here, left side it will point to 9, and 9 has no elements further. Then 10 will, next right of 10 will point to another node which will store 16, and this side no element, and this side we will have 11, and no more element in 11. So this is the tree, and if we store the data in this tree, then searching of element will be comparatively faster than array and the linked list. So this is another example where we can make use of the tree data structure.